An implant thinner than paper, capable of reading brain signals. This is not science fiction. It's an experimental technology being developed right now. At leading research centers in the United States, Columbia University, Stanford, and the University of Pennsylvania, scientists are creating ultra-thin, flexible neural implants. Their thickness is just tens of microns, thinner than a human hair. They are made from flexible polymers and can be placed between the brain and the skull, conforming to the brain's surface without rigid pressure. Inside these implants are thousands of microelectrodes. They record the electrical activity of neurons and allow researchers to study brain function with extremely high precision. Unlike rigid electrodes from previous generations, flexible systems cause less damage to brain tissue, trigger less inflammation, and remain more stable during long-term use. What matters is not only the number of electrodes, but also the materials used. Modern neural implants rely on conductive polymers, gold and platinum, graphene, and other two-dimensional materials. These electrodes can be comparable in size to neurons, sometimes even smaller. This reduces tissue damage and enables more accurate signal detection. One of the main challenges is data transmission. Current experimental brain-computer interfaces can transmit data at speeds of tens of megabits per second, usually via wired connections or experimental wireless systems with heavy data compression. Power supply and most signal processing are typically handled by external systems. This reduces heat and improves safety. A neural implant does not integrate into neurons and does not read thoughts directly. It sits on the surface of the cerebral cortex or beneath the dura mater, conforming to the brain like a thin film. Each electrode detects tiny electrical fields generated when groups of neurons activate together. These are not individual thoughts, but patterns of activity related to movement, speech, attention, or vision. Thousands of electrodes function like a sensory map. The more there are, the more precisely researchers can determine where and when signals occur in the brain. In the opposite direction, the implant can gently stimulate the brain using weak electrical impulses comparable to natural neural activity. This is how pathological signals in epilepsy can be suppressed or lost functions partially restored. For now, these are laboratory prototypes tested in animals. Clinical trials in humans for such ultra-thin systems have not yet begun. Neuralink, for example, has limited human trials, but it is a different type of implant with a different design philosophy. A full brain-computer interface is still far away, but technologies like these are gradually erasing the boundary between biology and electronics.